Okay, so in today's video, we're going to show that all convergent sequences of real numbers are Cauchy sequences. Okay, in particular, we're going to prove the following lemma. So if X is a convergent sequence of real numbers, then X is a Cauchy sequence. So before proving this, let's go ahead and state the tools that we'll need in order to show this. So we're going to assume that X is a convergent sequence of real numbers. So I think that, let me just say the tools that we'll need. We're going to need the definition of convergence. Okay. And then if we assume that a sequence converges and we use the definition of convergence, the next thing we're going to want to do is maybe show that it's Cauchy, and particularly we want to get an estimate. So on this. So we want to estimate this. For large values of n and m. Okay. And when doing that, I can imagine that if we're using the definition of convergence and we have an estimate on this, it's more than likely going to be the case if we're going to use the triangle inequality. And I think that should be it as far as the tools we'll need in order to prove this. Okay, so let's go ahead and get started. So proof. So let's suppose that X is some sequence of real numbers. So it converges. So let X be a convergent sequence of real numbers. I'll just say reals to shorten it up. With limit, say, X. So we're going to assume that the limit of X n is equal to little x. Okay. So now that we've done this, right, we can make use of the definition of convergence, and we know that for large indices n, xn is within some epsilon distance to the limiting value, right? So we can say maybe then for arbitrary epsilon greater than 0, there exists some index k, right? Some integer index k, such that n greater than or equal to k implies that the distance from the sequence value to the limit is at most epsilon over 2. And the reason why I'm choosing epsilon over 2, other than to be fancy, is just to say that I know that I'm going to look at the distance from that to the limit and the distance from that to the limit. Right? Like for large values of n and m, we know that that's close to the limit and that's close to the limit, which means that if we use the triangle inequality, we can squeeze those things together. And you'll see that now. So maybe thus, for n and m greater than or equal to k, we have, so now we're going to do the estimate part, right? We're going to look at the distance between these terms. But this, we're going to do that old trick now where we add and subtract the same value. So I'm going to subtract the limit, I'm going to add the limit, and then I have the xn term here. But now we can use the triangle inequality here and say that this is at most that distance plus this distance. But since n and m are greater than or equal to k, we know that the distance from the term to the limit is at most epsilon over 2. So this becomes epsilon over 2 plus epsilon over 2 equals epsilon. Hence, the distance between the terms of the sequence is small, arbitrarily small, whenever n and m are greater than some index value. So this is a Cauchy sequence. Yeah. Okay. So again, these are techniques that will appear over and over again in your real analysis course. Use definition of convergence. You want to estimate the distance between things. You want to apply the triangle inequality. You want to reference the definition you're seeking and repeat. So in the next video, we're going to show that all Cauchy sequences are bounded. And the end goal for this series of videos on Cauchy sequences is to precisely determine convergent sequences all over. In particular, our goal is going to be to show that convergent sequences are precisely Cauchy sequences. But in order to do that, we need this result, and then we need that the sequences are also, the Cauchy sequences are bounded, and then we'll present our final theorem on the Cauchy criteria. Thank you for watching.